Well, then wherever you put business. All right, everybody. Hi. Welcome back to another exciting edition of HotSci 2025, which is the summer colloquium series for here at STScI and JHU. Today, we're going to learn about nearby galaxies and circumgalactic media. Two excellent STScI postdocs. So without further ado, let's first welcome Dr. Sapna Mishra, STScI. He's going to tell us about the diffuse gas in the Magellanic stream.
All right. Good afternoon, everyone. I'm Sapna Mishra. I'm a postdoc in Milky Way Halo Group. I'm almost finishing my second year here in STScI. In this talk, I'll discuss about the spatial and kinematic distribution of the diffuse gas in and around the Magellanic system. Magellanic system is primarily made up of large and small Magellanic clouds, the two nearest satellite galaxy of our own Milky Way, and an extended gaseous stream, which we know as Magellanic stream. In this talk, I'll be mainly focused on the two questions. The first one is, if LMC holds its own circumgalactic medium, aka CGM, if yes, how big it is? And second, what is the distance of the gas to the Magellanic stream from us? The answer of these questions are crucial for the evolution of satellite galaxies in general. But before that, what is circumgalactic medium? All right, in order to honor our CGM tradition, I had to pick this iconic schematic of the CGM of a galaxy. Sorry, CGM folks. So CGM is a diffuse gas envelope surrounding a galaxy as shown in the white dashed circle. It connects the galaxy with a larger cosmic environment and helps regulate its evolution. And the way it regulates its evolution is through inflow of a gas from the accreting gas from the intergalactic medium and the outflow of a gas via stellar and agent feedback. And CGM, in particular for a satellite galaxy, is a first line of defense. It acts as a shielding layer which protects the gas inside the galaxy from being stripped away from the surrounding environment effect from its host galaxy. All right, moving with this, we all know LMC is the nearest satellite galaxy of the Milky Way, and it is moving through the CGM of the Milky Way. As it approaches, the relative motion of the LMC through this dense medium causes ram pressure stripping of the LMC gas. We observe this stripped gas as a Magellanic stream trailing behind the clouds. But one of the big questions to ask here is, can LMC hold on to its own CGM under this harsh environment? By the way, this is me. My phone has created this. So recent studies have shown that LMC has halo mass of more than 10^11 solar mass. And we know that isolated galaxies of this halo mass do have their own CGM, which even extend up to 100 of kpc. So what is happening to the LMC CGM? We'll learn shortly. But one of the big challenges in the study of the CGM is it is too faint to be directly mapped in emission. We will learn about the CGM in emission in detail in Vida's talk, but to probe CGM to probe diffuse gas of the CGM, in general, the common method is to study in absorption in the spectra of a background quasar. The idea is very simple and is shown in this. You find a quasar behind the galaxy, and as the light passes through the CGM of the intervening galaxies, and you look for a CGM absorption at the velocity or redshift of this galaxy, and this is how you probe the CGM of a galaxy. And shown here, this simple schematic shows this idea in context of the LMC, where diffuse gas around the LMC is being probed using spectroscopy of the background quasars. But in reality, this setup looks like this. Shown here is the H1 emission map of the Magellanic system in the galactic coordinate. This map is color-coded with the column density of the H1 gas taken from the Westmeyer 2018. The stars on this map are the location of the 28 HST cos quasar sight line taken from a study led by Krishna Rao 2022. These sight lines are color-coded by the projected distance from the LMC center, which we also known as impact parameter. And as can be seen from these quasar sight lines, they probe the LMC CGM from 3 kpc to 35 kpc from the LMC center. But the main focus of the Krishna Rao 2022 study was to map the Magellanic corona, which is a hotter ionized component of the LMC CGM. The author used 3 high ionization UV absorption lines, C4, silicon 4, and O6, to study the Magellanic corona. Shown here is the column density profile of these 3 ions as a function of impact parameter from Krishna Rao 2022. A clear decline in the total column density of these ions with LMC distance can be seen here. And from this, which is a characteristic trend expected for a CGM of a galaxy. With this, author gave the first direct evidence for the Magellanic corona. Building on to that, we revisited the same sample, but focusing on tracing the school CGM of the LMC traced by transfer 4 Kelvin low ion UV absorption line. Our main aim is to map how far LMC CGM extends. So with that, we gathered and combined the G130 and 160 spectra of each quasar sight line, and we look for the absorption from the 17 absorption species from the 7 low ion UV absorption lines, as listed here. Shown here is the silicon 2 1526 absorption profile for one of the quasar sight line at 8 kpc from the LMC. We only focus on the region beyond 150 km per second, which is marked here by the dashed red vertical line, to avoid the contamination from the Milky Way CGM. And then we fit these absorption profile using VPFIT to calculate this velocity centroid and column density of each component of this absorption profile. And we did that for 7 absorption line from this 7 UV absorption, 7 low ions, and in all the 28 quasar spectra. Next, we explore the variation of total column density as a function of impact parameter. Here I'm only showing the results from the 4 ions from low to high ionization state as marked here, silicon 2, silicon 3, and 4, and C4. And on the x-axis, I am plotting the impact parameter, and on the y-axis, I'm plotting the total column density of these ions. These are the measurements for the total column density. The data points with arrow pointing downwards are the upper limit from the non-detection, and the data points with arrow pointing upward are the lower limit from the saturation. And next, we fit these profiles using power law and the censored probabilistic Bayesian approach. This approach takes into account both lower and upper limit in the data while fitting. So from these profiles, 2 main results can be noticed. One, we see in all the ions a clear statistically significant declining trend in the column density as a function of impact parameter, as can also be confirmed from the significant slope of these power law. And second, and this is again to remind you characteristic signature for a CGM of a galaxy. And second, LMC not only has its own CGM, but it is also multi-phased. Next, we explore how the LMC, next to explore the effect of environment, we compare the CGM profile of the LMC with the isolated dwarf galaxies. For that, we took the column density relation from a recent study by Zhang 2024 for the dwarf galaxy. And on the x-axis, now we have a normalized impact parameter, and on the y-axis, we have total column density. And again, I'm only taking the results from the Zheng et al. For the ions, which we have considered in our study. So these are the column density profile relation from the Zheng et al. For the dwarf galaxies. And they derived this relation using a sample of 56 dwarf galaxies from mass ranging from 10 to the power 6 to 10 to the power 9 solar mass. And corresponding LMC profiles are shown in red in each panel. So the main key result from this, you see that the profile of the LMC for all the ion declines more sharply compared to the dwarf galaxy sample. And if at all, halo mass is the dominant factor, which we know since more massive galaxies tends to have more extended halo, LMC, which is more massive than the dwarf galaxy in their sample, should be having flatter profile. But instead, we see a sharp decline in the LMC profile, which could be due to the strong environment effect from the Milky Way. Next, we explore the kinematics of these UV absorbers as a function of impact parameter. Again, I'm showing the results for 4 ions. And on the x-axis, we have impact parameter, and on the y-axis, we have centroid velocity of the individual component of the absorption. These are the velocity centroid of the individual component in each quasar sight lines. So what we see here is the sight line which are probing inner LMC region have more number of components compared to the sight line which are probing outer LMC CGM. This indicating the inner CGM is more complex compared to the outer CGM. And next we explore how this velocity centroid is distributed relative to the systemic velocity of the LMC, which is 280 km per second, and is shown here in the dashed horizontal line in each panel. The gray band in each panel corresponds to plus minus 50 km around the LMC velocity. And next, what we did, we estimated the column density weighted centroid velocity for each quasar sight line. And what we see, and they are shown in the dark red star, dark blue star in each panel. And what we see here, we notice a jump in the centroid velocity at a distance relative, like almost 17 kpc in all the ions. And what this jump tells us, that the absorber within 17 kpc have velocity which are consistent with the systemic velocity of the LMC. While the absorbers which are beyond 17 kpc, they have lower velocity compared to the systemic velocity of the LMC. And we see this in all the ions. And next we explore how this compares with the velocity of the H1 gas. So to do that, what we do, this is the same H1 emission map of the Magellanic system in the galactic coordinate, but this time it is color-coded by the VLSR velocity of the H1 gas. And the quasar data point here are color-coded by the velocity from the absorption line studies. And for the visual distinction, the sight lines which are within 17 kpc, I show them with this circle, while the sight line outside 17 kpc are shown in star. Here also we find a similar trend. UV absorbers are tracing the H1 gas first, and second, the H1 gas which are within 17 kpc, they have velocity consistent with the LMC velocity, while the gas outside the 17 kpc, they are being dragged behind and slowed down to the lower velocity. From this, we conclude that LMC CGM has two components. The one inner CGM extending only up to 17 kpc, and the outer extended CGM, the stripped region, may be associated with the Magellanic stream. And at the end, we conclude that the LMC inner CGM with radius 17 kpc is extremely compact. And this truncation radius is actually consistent with the simulation of the ram pressure prediction of the LMC gas by the Milky Way CGM. And it's like a Milky Way is acting like a giant hairdryer in the background, and which is blowing gas off the LMC. And we actually had a NASA press release on these results where we presented this analogy like Milky Way acting as a giant hairdryer in the background, which is blowing off the gas. And if you want to look more about this press release, you can get it from this, you can scan this QR code. And I asked AI to generate an image for this analogy, and this is what it gave me, which is like really cool. And the fun fact that this analogy was recently featured in the Jeopardy earlier this year, which was pretty cool. And yes, the contestant got it right. All right, if you look into the sample of our existing 28 HST cost quasar sightline, what we notice here that majority of our quasar sightline are probing the backside of the LMC towards the Magellanic stream, while the front side of the LMC has no observational coverage. And this side of the LMC is particularly important because this is the region where the CGM of the LMC and the Milky Way is colliding. And this collision can also alter the physical condition, can drastically alter the physical condition at this interface, and could even give rise to bow shock, which simulation also suggests that. But this region is also suffering from a large galactic extension, and it is very hard to find UV bright quasar in this region until now. Thanks to the recent plain quasar catalog by JHU, we look for the new quasars in this region, and actually we found 5 quasar sightline probing this region. We proposed these sightline in the HST cycle 32, and we were awarded 29 orbits for this. And the observation of these 5 quasar sightline will take place in September. So stay tuned for the new exciting results for the LMC front sightline. All right, this brings to my second part of my talk, which is distance to the Magellanic stream using optical spectroscopy of the star. All right, one big unknown about the Magellanic stream is its distance. We still don't know how far is the gas from us, actually. But the distance to the Magellanic stream is important for the following reason: to constrain the origin of the Magellanic stream. There are some studies which suggest that stream is formed well before LMC and SMC entered into the Milky Way and putting it to a distance of 100 kpc from us. While there are some studies which says the stream is formed when LMC and SMC entered into the Milky Way and shaped by the ram pressure stripping, which places the stream as close as 20 kpc from us. But still, we don't know the distance to the gas of this Magellanic stream. And second reason is, this stream of gas carries a massive reservoir of 10 to the power 8 solar mass gas. And if this gas reaches to the Milky Way, it can fuel the future star formation. And also, there are many physical properties like cloud mass, size, pressure, and density. They scale directly with the distance. So if we don't know about the distance of the gas, we cannot reliably estimate these parameters. So pinning the distance of the gas of the Magellanic stream is really important. So to do that, we have used very simple but direct method. So shown here again is the H1 emission map of the Magellanic stream, but this time shown in the Magellanic coordinate. On the x-axis, we have Magellanic latitude, and on the y-axis, we have Magellanic longitude. And LMC sits at 0, 0 in this coordinate system. All right, and then we focus on the region along the trailing stream of the Magellanic stream, which has a H1 column density of more than 10 to the power 18.5 per centimeter square. And then we search for blue horizontal branch stars with known precise distances in those regions. We use the SDSS Blue BHP star catalog from ZOO 2011. And we found 5 blue horizontal branch stars with precise distance known in the 2 regions of the Magellanic stream, which we mark as group 1 and group 2. And we have 3 BHB stars in group 1 from distance ranging from 13 to 42 kpc. And we have 2 stars in group 2 with distance 20 to 55 kpc. And next, we observe these stars with VLT UVES to get their high resolution spectra and to search for calcium 2 and sodium 1 absorption. We also used the 5 archival VLT UVS spectra of the quasar sightline, which were also passing from this stream. And we used this quasar sightline, which I will explain later in my talk, to give the maximum predicted column for a given velocity location of the Magellanic stream. And the idea is really simple. You take the spectra of the star, you look for the absorption, optical absorption, say calcium 2 and sodium 1, at the velocity of the stream. And if you see this absorption at the velocity of the stream, you say the stream must be in front of that star. And if you don't see any absorption in the star spectrum, stream has to be behind that star. And we have used multiple stars actually because we are trying to narrow down the distance to the stream in case there is some curvature in the stream or clumpiness in the stream. Therefore, taking different star would be important. And these are the normalized VLT UVS spectra of 5 of our star sightlines, and for the calcium 2 absorption. And this is where you would expect the absorption from the stream in these 5 star spectra. And from there, immediately you can see we did not detect any absorption in all these 5 star spectrum at the stream velocity. We also measured we also estimate the measured column of the calcium column by simply integrating the stream region within a window of 3 resolution elements for all these stellar sightlines. Next, we also predicted the calcium absorption from the quasar sightline at a given NH1 and at the stream velocity. And they are shown in the solid red curve in each panel. And then to quantify the non-detection, we define a quantity called delta log n, which is predicted minus measured columns of absorption. So the idea is if the delta log n is more than 1 dec, we take the star distance as a firm lower limit on the stream distance. And this more than 1 dec assure that the measured absorption is at least 10 times smaller than the predicted absorption. And if the delta log n is more than 0.3 dec, we put the star distance as a tentative lower limit onto the stream distance. And if it is delta log n is less than 0.3 dec, the stream distance is inconclusive from our study. You can see from the delta log n value in all these stars spectrum, we have in 4 out of 5 cases, we have delta log n more than 1 dec, indicating that we can use these stars to put a firm lower limit onto the stream distance. And we also stack the stars from these different groups to generate a stack profile in the rest frame of the stream using FNR weighted stacking analysis. In the top panel, I show the stack of the group 1 star, and in the bottom panel, I show the stack of group 2 star. While stacking analysis do increase the spectral sensitivity, we still do not detect any significant absorption at the stream velocity. And this can be further confirmed by the delta log n value of more than 1 compared to the predicted absorption from the quasar sightline. Therefore, to summarize, here I'm plotting the delta log n values as a function of distances, and the data points for the star distances are shown in star, and the data points for the stack profile are shown in square. And as can you see from both stars, individual stars and stack profiles, we get the non-detection with delta log n more than 0.3. And from this group 1 star, we put a firm lower limit, which goes up to 40 kpc, 42 kpc for this, and which is delta log n is more than 1 dec here. So from group 1 star, we put a firm lower limit of 42 kpc for the distance of the stream. And then for the group 2 star, we put a firm limit of tentative limit of 55 kpc. This is the first observational constraint for the distance to the stream in the Magellanic stream, distance to the gas in the Magellanic stream. And these distance constraints will be very crucial input in the dynamical modeling of the XMC system. But still, we have only lower limits on the stream distance because it is very hard to find bright BHP star at faraway distances. With new DAISY BHP catalog, which doubles the existing catalog and will be public next year, we may find some bright BHP star beyond 55 kpc. That's the hope because it's still not public. And for future observation of these faint faraway BHP star will be a crucial target for the upcoming facilities like ELT and HWO. So with this, I'll stop my talk and I'll leave you with this summary slide. Thank you.
All right. So, what questions do we have?
Can you maybe comment a little bit on that second figure you have up there, the lower ions look much more dramatically different than higher ions?
Yeah, because high ion gas is actually more diffused, and it's like, but the low ion gas is more like constrained to the inner part, and all the gas which are like in the low ion, like if you strip the low ion gas outside, the part will be dramatic because there are already less gas in this region and more gas in this inner region. But the hot gas is actually diffuse overall, so more uniformly. As you can see, even the slope of the hot phase was like less than even like in the full profile. So it's because of the diffusivity of this gas. Yeah.
Given that the LMC CGM is also in the Milky Way CGM, how much potentially is the Milky Way CGM contributing to the absorption that you see for the LMC?
We are actually not taking by putting the velocity cut, we are not including the absorption from the Milky Way CGM. Like, for example, like here, like this is the absorption from the Milky Way CGM. So if I'm only taking the absorption from the, yeah.
So the Milky Way is blowing the stuff away from the LMC. This is definitely not my area. So how long would that take to have a measurable effect on?
That is the good question. Maybe simulation people. I don't know about that, but interesting would be like the way I think this is like get a galaxy which is far away from get a satellite galaxy which is even farther from the LMC, like from its host, and see how its CGM is compared to the one with the LMC, and just compare and try to.
Well, for example, how would that compare to the time scale for the LMC to orbit the Milky Way? Would it change dramatically if time went around, or would it just kind of be like that?
Yeah, I don't know about that. Yeah. But definitely a good question.
Questions?
So the LMC itself is about like 50 kpc, right, away from us. And you're saying that the lower limits on the distance for the stream are at least in the 20 to 40 kpc. Right?
Oh, this is lower limit, yeah.
Lower limit,
Yeah, so it could be far away, up to 55, like.
Up to 55, yeah, I guess you're saying based on the, ramp pressure stripping argument, you would expect, though, the stream to be
yes,
the LMC and
the closest distance.
Yeah,
the closest distance of the LMC could be, this is like in one of the existing studies in 2021 by looking. But yeah, but we are sure the stream is beyond 55 kpc.
Okay.
Yeah.
Thanks.
Okay.
One more question. Oh, that's fun. Are you showing like radio profiles?
Yeah.
Or radio. I don't know if you talked about sort of like and has a means of dependence, because these interactions, as I understand, gas would sort of be stripped away in a sort of non-isotropic fashion, right?
Yeah, I have not done that. Yeah. What is the inclination of the, let me see. I don't know. I have not looked into this. Yeah.
Is this one? No. Okay.
Next, we have Dr. Vida Saeedzadeh from STScI. Please go.
Yeah, thank you. Hello, everybody. My name is Vida Saeedzadeh. I'm a first-year postdoc with Foggy Collaborations. I'm basically based across the street at JHU, but you see me here a lot since I'm working with Molly Peoples and Jason Tomlinson on the first floor. Today I'm going to talk about a project that I started from the beginning of my postdoc and work with Foggy about looking at the CGM in emissions, testing its observability and what we can learn from the CGM in emission. It's an ongoing project, so I'm really looking forward to have any comments or feedback that you have or things that you think that would be interesting to see, and I'll be adding to these projects, so I would be very happy to discuss it afterwards. Okay, so by having that in mind, let's talk about the CGM. So circumgalactic medium is a complex environment. I don't think that I have to convince anybody here, especially after a great talk from Sapna, that's like CGM has a very important role in the evolution of the galaxies. It's a place that the galaxies get their gas to fuel the star formations. It's the destination for the outflowing gas to go to this environment. Some of the outflowing gas from the AGNs and supernovae, they go to the CGM, they become part of the CGM, or some of them recycle back and contribute to the evolution of the galaxies again. So there is a constant interactions between the galaxies and their surrounding halo. From the first time that it was noticed the CGM was noticed in 1960s, there has been tons of studies about, like, from the theory, from simulations, and also observations to study its nature and its role in the galaxy evolutions. But despite all these studies, the most complete pictures that we have today from the CGM is just a cartoon. But what we want to do is actually, we want to retire this cartoon. So, we want to, and I'm quoting Jason Tomlinson himself here, that we want to retire this cartoon, and we want to take the steps to a real image. Can you imagine that go to a CGM talk and they are not showing you the cartoon anymore and actually show you a real picture? That would be very nice. But that's a long way. It's a very difficult problem to solve, but I think we are in a place to start taking the steps towards that destination and towards getting a real image of the CGM. So, so far, most of the knowledge that we have about the CGM is coming from the absorption line studies. This is a very powerful technique to detect the low density gas and the CGM, and it gave us a lot of information. But it has its own limitations. It has, like each of the galaxies usually have only one sightline. It's also limited to the number of the quasars that we can find. So we can only study the CGM of the galaxies that they have a background source. So we have to average over mass, over the radius, over the redshifts, and this kind of like smooths out a lot of details and structures and like informations that we can get from the circumgalactic medium. So to be able to fully map the CGM, we need to map it, like have a 2D complete map, not just like pencil beams informations. And for taking that step would be looking at the emission, looking at the CGM in emission. The emission study can give us a complete full projections of the CGM about of all of the galaxies. We don't have to rely only on the galaxies that they have a background source. We can observe, we can study the circumgalactic medium of any galaxies that we can observe, and that gives us a lot of information to be able to complete our understanding of the CGM. But so if we want to look at the CGM in emissions, then the next question would be, what are the lines that we want to look at? So CGM is a multi-phase environment. It spans a few order of magnitude in temperature and density. It's has like, so to be able to actually recover all this all these multi-phase structures, we need to look at the all of the range of the ions from lower ions to higher ions. And if specifically we are interested to look at the CGM and follow the lines that can describe the CGM, especially in the lower redshifts, then we need to look at them in UV emissions. So to be able to actually make some predictions from these possible emission observations, and also help designing the instruments that are able to see the CGM in emissions, we need theoretical models that can resolve the CGM at the first place. So foggy simulations are very well suited for studying the CGM because of their very high resolution in the gas around the galaxies. So traditionally, the methods that are used in the simulations is that the resolution is relative to the density of the region. So in higher density regions, you will have higher and higher resolutions. Therefore, you will miss the high and good resolutions in the environments like the CGM, that is low density gas. But what foggy has, it has a very novel model that it has a box around the galaxy that will resolve everything in a very high resolution inside that box. And in addition to that, every region that has that is cooling fast, basically has a cooling time less than its local free fall time, that will also be resolved in a higher level. So that in total will give us high resolutions in the CGM and a lot of details that we could not see before. So I use the foggy simulations to look at the emission lines in all these different ions, from higher ions like oxygen 6 and carbon 4 to the lower ions like magnesium 2 and silicon 2. As we can see, even by looking at these maps, you can see there are differences in the morphology of these of the CGM that each of these gas is tracing. If I zoom in, you will see, for example, a loop shape, for example, shape here in that is followed in H alpha. Okay, sorry. In H alpha, and while you in oxygen 6, you just see a diffuse gas. It's also true for carbon 4 and silicon 4, but you start seeing that shape and structures more in the lower ions. And for example, in magnesium 2, it's more like a few clumps other than a whole loop. So that is what I'm trying to say is that if you look at one of these lines or a few of these lines, we never get a complete picture of what's going on in the CGM. So we need to observe a high range of the ions and that follows different temperature and density to get a better picture. Okay, so I had that. Yeah. Okay, so the other thing that I looked at is that the surface brightness profile of the different lines in the CGM. So first, I looked at the all the gas that is in the simulations in these boxes that I am showing you, and afterwards I also did another experiments by removing the H1 disk from my simulations data and showing that just the emission profiles without the disk, and that would be only the CGM gas. So you can see that interestingly, a kind of a break that can be seen from this like solid line from the inner regions to the CGM or outer regions, and these are the kind of things that can be observable if we can observe the CGM in these different lines. And this is just true for the lower ions. Okay, so so far I was trying to show you that it's important to observe and like study the CGM in emissions and what kind of information it can provide for us. But the main question is actually that can we observe the CGM in emission? So for the rest of the talk, I am going to do some experiment and explorations with the different capabilities that an instrument needs to have to be able to observe the CGM in the emission. I start by looking at the spatial resolutions, one of the most important criteria of an instrument, and how that affects observing the gas in the emission. So first you see the map from the foggy simulations in its own native resolution with about 0.27 kiloparsecs, and then I made the same map for coarser and coarser spatial resolution, and you see that a lot of details and structures that you can see here are all smoothed out in a very high resolution, but still at 1 or 3 kiloparsecs resolution we can still see many of those structures, or at least like a sign for them. But in addition to the spatial resolution, what is important for an instrument to be able to observe the gas in the CGM, it's their sensitivity, it's their detection limit, how good they are in detecting the gas in emission. So if I have observations from, like if I have an instrument that observe the galaxy in a fixed sensitivity, and I also only change the spatial resolution, you see that like I'm losing a lot of details. But if I have that for a specific spatial resolution and for worse and worse sensitivities, I will lose a lot of gas around the galaxies and won't be able to observe them. So so far we have some instruments that can be used to observe the CGM in the simulation, in the observations. For example, I'm showing just as an example here MUSE that like will be sit here in this chart, but there are small upcoming CubeSat and satellites that are kind of focusing on the lower redshifts, and they are pushing for better sensitivities and spatial resolutions. So ideal place to be is over in this corner, but we are still trying to like complete this, I guess, like this chart and getting to this place to have the best picture that we can have from CGM. Okay, so if I want to quantify what I was showing with the changing the spatial resolutions and sensitivities of an instrument, here I'm showing you the observability of or like how much of the gas in oxygen 6 as an example of a high ion, and like magnesium 2 as an example of a low ion in the CGM, depends on what my instrument spatial resolution and sensitivity is. So in the best case scenario, you can see we can recover more than 90% of the magnesium 2 mass, but for oxygen 6 it's only about 25%. If you go to the other end of the spectrum, in the worst case scenario that I have in my analysis is we only can basically recover about like 2 or like a couple of percent of the mass of the oxygen 6. So it shows how complicated this is, but if I focus only on for example, the fixed sensitivity and change, see how does it change by like going to higher and higher spatial resolution, you can see that like this number decreasing in both of the cases, but it's not decreasing as fast as if I look at a fixed spatial resolution and changing my sensitivity to a higher and higher number. So that shows us that if we want to push for something in making or like designing an instrument, if we have a good spatial resolutions, where we want to push more is basically increasing the sensitivity of the instrument. Okay, so far I talked mainly about like the detection of the CGM in emission and its observability, but we cannot retire this cartoon only by detecting the CGM in emission. We also need information from the kinematics and dynamics of the gas and what's happening around the galaxies. So for that, in the next part of the talk, I'm going to focus mostly on the velocity predictions, and by asking first like that for looking at the different ions and their velocities, how they are differ, and what kind of spectral resolution we need to be able to actually distinguish these gases from each other. So I'm going to take my time to explaining this slide a little bit. So here I'm showing the two projections of the emissivity weighted projections of line of sight velocity of H alpha and oxygen 6. And even by looking at these two maps, you can see that these gases are following these ions are following gas with different velocities. So if for each line of sight, if I take these two maps and find the differences between the velocity in oxygen 6 and H alpha, you will see the result in this gray map over here, which basically shows me that like depends on what kind of spectral resolutions that my instrument has, I would be able to distinguish these two ions from each other or not. So basically what I'm showing here is that this sight line, if I have, I'm showing both H1 and oxygen 6 as the velocity profiles. If I have a very high spectral resolutions, everything will be on top of each other. Basically, I cannot distinguish them from each other. But with a higher resolution, that's when I'm going to see for the exact same sight line being able to distinguish the two ions. So this is showing like more and more colored gas is basically showing you that what kind of spectral resolution we need to be able to distinguish the oxygen 6 and H1 in everywhere here in the field of view. So this is showing basically that the H1 and oxygen 6 trace very two different phases, but even though they are having very different velocities, we have we need like high spectral resolutions, about like 30 kilometers per second or so to distinguish them. But like for a gas, like for example H1 and magnesium 2, which they both trace the cold gas, they are more correlated kinematically, and even like 30 kilometers per second resolution is not enough to distinguish the two gas kinematically from each other. Next, I am going to show you the another way of like how the spectral resolutions play a role to be able to distinguish the velocity components when I'm looking at a gas in emission. So here I'm just only showing oxygen 6, but what I did was that I used the simulations 3D informations to define inflowing gas, which is gas with radial velocity less than 100 kilometers per second, and the outflowing gas, which is a gas with velocity more than 200 kilometers per second. I have them in two different groups, but if I look here again on the same line of sight velocity, you will see that they are showing like two different components in the line of sight in the velocity profile. So if I get, so what I'm doing, showing exactly in each of these maps is basically the emissivity weighted average of these profile for each of these components. And I will find what is the differences between these two average, and I show that as a pixel in the final plot. So this way I can explore that what kind of spectral resolution I will need to be able to differentiate two different velocity components in a gas in emission, for example, that I'm looking at it at, for example, the oxygen 6. So we need high. If we go higher and better and better in the spectral resolution, we cover higher and higher amount of the field of view to be able to do distinguish these two. Okay, so if I can bring everything together, then that would be this example that I'm showing here. So, for example, if I have a very high, an instrument with very high spatial resolutions and a good detection limit about like 100 photons per centimeter square and so on, this would be, the pink color would be something that I see around that galaxy. But does that mean that like I can kinematically also distinguish the inflowing versus outflowing gas in this gas that I'm observing in emission or not? That's also really depends on the, again, like the spectral resolution of my instrument. So again, if I have not very good spectral resolutions, only about maybe 50% of this region that is already I detected in the emission can be resolved kinematically between the inflowing and outflowing gas. And if I have a better and better resolution, then, sorry, I have to build it again. Better and better resolution, then, I don't know really, please. You get the point. Yeah, the better resolution is better. So we can cover about like 100% of the region that we already observed in the emission. Yeah, so that will bring me to my summary or the conclusion plot. So retiring the cartoon is not that easy. No wonder that we haven't done it yet. So it is a very difficult, multi-dimensional problem that we need to solve. I showed you that the emissions can help us to observing the CGM in emission can help us to complete our picture of the CGM. But there is hope. There are currently some instruments that are able to observe the CGM in the emission. There are upcoming missions that are basically working on to specifically focus on the looking at the CGM in emissions. And I showed that to be able to actually have a complete understanding of the CGM, we need to cover a big range of ions, from lower ions to the higher ions. We need about a very high sensitivity in our instruments, maybe less than 500 photons, very good spatial resolutions, maybe around the 1 kiloparsecs. and also very good, less than maybe 50 kilometer per second spectra resolution. So that would be the ideal corner that we want to have to be able to see the CGM and resolve everything in the best way that we can. There are, as you can see, there are some upcoming missions like the Juniper here, that's like Emily Witt in JHU is leading, have very high spectral resolutions, and other satellites that is basically pushing for better and better sensitivity. But the question is, can we make an instrument that meets everything? And maybe we can. So by that, I'm leaving you by this conclusion, and thank you for listening.
All right, we have time for a few questions for Vida. So, any questions to start off? I think you went through this.
Yeah. So in this figure, the green, is that for like detecting O6 or for magnesium 2, which seems probably the most easiest one to get?
Yeah, very good question. Yeah, so this is basically for for the faintest one that we can see, which is like mostly the more diffuse, like higher ions. The lower ions, like magnesium 2, they are like easier for detection. So maybe even like lower sensitivities can still like kind of like basically make us be able to resolve like or recover a lot of the gas in those lower ions. But yeah, so this is the restricted, I would say, measures.
Yeah, so early in your talk, you showed that the low ions had these breaks in their surface density profiles.
Yeah.
Could you describe like what's causing those breaks? Is there some truncation going on, or do you understand why they have that drop?
Yeah. I am getting it. Okay. Yes. So I think that's one thing that helps us kind of explain what is happening here is basically even removing the main like the central disk from the analysis. So here, like it shows, like most of the lower ions, they are very concentrated in the inner regions, like inner halos. So when I remove that shows that like it has, like compared to the higher ions, like oxygen 6, that you can even see in these like maps that they are already very diffuse. So they are already very diffuse. So a lot of like these gas, like the profile that you see, it doesn't change that much. So, but like for the magnesium 2 or like lower ions like silicon 2, you can see exactly even by eye that there is tons of like a higher amount of emissions coming from the central regions. So that makes the break, if that makes sense. Yeah.
Can you go back to the heat maps you showed?
Yes. I have to build it. Maybe I can do this here. This one?
Yeah. So is this just for one halo?
No, it's the average among 6 halos in Foggy. Yeah.
Do you have an idea? I'm curious how the dependence on the spatial resolution, how that varies between systems. Even if the CGM has different scales of clumpy material and stuff.
Yes. Yeah.
Do you know how much that spatial scale changes?
So I saw the same trend basically in all of the halos. So like going to the higher spatial resolution and sensitivity will decrease the amount of the basically mass you can recover. But the actual numbers, yes, they change. So it's not like maybe if I do that like halo by halo, that would not give me exactly like 38% decrease. But we still see that decrease in all of the halos. Yeah. Similar order, yeah.
Questions? Yeah.
Sorry, going back to the different morphology. is this also pointing to like different ionization mechanisms? Like the lower ionization species like magnesium being more ionized by like making photons versus O6, which is maybe something else going on.
Yeah, so that can be one of the reasons, like that's like different ions in different stage, like they go through the different mechanisms. But so for this specific, like I'm doing like post processing for the simulations data. I'm using like Cloudy, which is including the photoionization. So basically the same kind of mechanisms are considered for most of the ions here. That's a very good point. Like that would be more realistic to basically have like all of the mechanisms. But yeah.
So collisional ionization is not assumed for even for optical sense.
I should double check, but I think that's also just for photoionization. Yeah.
Right. If there are no other questions, I think we can. That's fast afterwards. Ice cream also.